So welcome again to our virtual pre-lab lecture. Today's lab is on method of initial rate, and I believe you have covered this concept in chemical kinetics. It's chemical kinetics. These labs fall under the chapter in the lecture chemical kinetics method of initial rate. Like I said, rate of reaction, all right? Rate of reaction is a function of, either one reagent or two reagent or even a product. You can look at the rate of reaction as a function of, let's say, A reacting with B to form C and D. Rate of reaction can be monitored as change in concentration of A over change in time. It could be also change in concentration of B over change in time. Rarely will you see that rate of reaction is monitored through the product. Generally, the rate of reaction is monitored as a function of the product. Reactants. So this is the rate of reaction. You can also look at the rate of reaction as a function of both reagent, and we call this rate law. A raised to some function or some value x, and B raised to some value y. This is called the rate law. We call this rate law, okay? The lower one here, we call this the rate law, which look at the rate of reaction as a function of both reagents, okay? There is integrated rate law. There is integrated rate law, which look at the rate of reaction with the component of time. You're gonna talk about that. So today, we will determine the reaction orders of our reactant, that is the value for Y and X. All right, and occasionally you may be asked even to find the rate constant. You know what we call this, where K we call X, and Y we call this reaction what? We call this reaction orders in the integrated, in the rate law. K, we call this rate what? Rate constant, rate constant. For those who joined us, I had started working an example on how to use the method of initial rate. Before I show you what you will need to do, there was an example I was working, showing you how to use the method of initial rate to find the rate orders, How are you going to find the rate orders X and Y? X and Y. This is our equation. Rate equals to K into A and PC. This is what we will be looking at today, X and Y, reaction orders. Let me see if I can pull you see here at the end, right here. Let me just show you so that you can talk what I'll talk about with the data sheet. If you look at, once you collect the data, you'll determine the reaction order with respect to A, with respect to PC, with respect to PC. If you look at the equation on my whiteboard, there is the PC here, and then there is the what? There is the A. We need to find, the objective of this lab is to find this and to find the value for Y, which is reaction order with respect to A, which is X, with respect to PC, which is Y. Let me just put this a little bit. This is the Y I am talking about. So how do you use method of initial rate? How do you use method of initial rate? From the word initial, all right, From the word initial, that means at the beginning. You measure the rate of reaction initially. You measure the rate of reaction initially. And I was about to get done with an example I was using to show how method of initial rate is used in determining the rate orders. Is used in determining the rate orders. So what I will do is first work an example on how to find the reaction orders. And here is an example. Let me see. There was an example here on how to find the reaction orders. All right. Let me show you how to find the reaction orders. There was an example here. If you look on your screen, the problem is we need to find the rate constant. We need to find the rate constant for this reaction. There is no way you can find the rate constant unless you use the method of initial rate to find the reaction orders, all right? And reaction order with respect to the first reagent, with respect to the second reagent hydroxide, in order to get the rate constant. Let me show you how method of initial rate. I'm going to minimize this. Let me just minimize this, submit, so that I can have access to my whiteboard here. I will write that equation as rate. This is the rate law for that reaction. K, which is the rate constant, times A. Let me use A instead of the chemical formula here. Instead of this chemical formula, times, all right, times the concentration of B, which is for hydroxide, raised to, all right, times the concentration of hydroxide raised to X. This is X, and this is Y. Remember, we are looking at the rate constant, which is K equals to question mark. How are we going to find the rate constant? Rate constant is given by rate. If we know the rate, all right, divide the concentration of A raised to what? Raised to X times concentration of B raised to Y. For this problem here, to find the rate constant, you have to find the value for Y, find the value for X and Y, so that you plug it in this equation to get the rate constant. You know how to rearrange the equation to make it the subject of the formula. So let's get started. Method of initial rate, to find the value for Y or X. Let's start with X. All right, to find the value for, X, all right, in method of initial rate, to find the value for X, which is for the first reagent, you got to look at, all right, you got to look at two experiments. This is experiment 1, this is experiment 2, this is experiment 3, with each rate. This is the rate, experiment 1, experiment 2, experiment 3. I have 3 experiments in this example. To find the value for for X, you pick 2 experiments. Remember, X is the exponent for first reagent. You look at 2 experiments where the concentration of the second reagent is constant, while the concentration of our first reagent is changing. In this case, we cannot pick. All right, we cannot pick 2 experiments where both reagents are changing. Or we cannot pick experiment where both reagents are constant. It's not gonna work. So the key for method of initial rate to work is pick 2 experiments. The other one is constant, the other one is changing. In this case, I'll say experiment what? Experiment 2, experiment 2, and experiment 1, where the concentration of A is changing, but concentration of B is constant. So you say rate 2 over rate 1, all right, equals to K2 over K1 times concentration of reagent A for experiment 2, raised to X over concentration of A, all right, raised to X, and then concentration of B is constant. It is 0.25 raised to Y, 0.25 raised to Y, raised to Y. So what will happen here is experiments, even though you run it, 10 times at the same temperature, rate constant will not change. So I will cancel this because it is the same, not gonna affect anything. And since this one is constant, it will cancel out. It will cancel out. So always K and K will go away. What will remain is the reaction or the concentration of the reagent A, 25 raised to X equals to rate 2. If you look at the rate 2, I'm getting these values from here. Rate 2 is 2.2 times 10 raised to negative 4. 2.2 times 10 raised to negative 4. This and this will cancel, will remain with 2 raised to what? 2 raised to X equals to, this is 1. This should be 1 right here. This is 1. Rate 1 is 1.1 times 10 raised to negative 4. So this will cancel, like it in your calculator, you end up with 2. You end up with 2. I know, all right, I know you can figure it out that the value for X is 1. The value for X is 1 by just inspection, by just looking at that, it's gonna be easy, it's 1. But in the event that you want to do calculus or algebra, you take the logarithm of both sides by saying that 2x equals to 2. You take the logarithm of both sides. X, I'm just bringing the 2 here. I'm bringing the x down and say x log 2 equals to log what? Equals to log 2 like that. I divide by log 2 both sides. I divide by log 2 both sides like that. This and that will cancel. X equals to 1. Any number divided by itself end up with 1. So I know the value for X equals to what? X equals to 1. What I've done here, I've used method of initial rate. Remember to use the logarithm on both sides, So once you're done with, all right, once you're done with your reaction order for that particular reagent, you go and do the inspection to find the order with the other reagent to find Y. That is for the second reagent. For B, I will pick 2 experiments where the concentration of B or second reagent is changing, but the concentration of the first reagent is constant. If I look at this, experiment 3 and experiment 2. Experiment 3 and experiment 2 are my experiment I'm going to use to find the value for Y. So in a similar fashion, this will be rate 3 over rate 2 equals to what? Equals to K3 over K2. Concentration of A in experiment 3 is 0.50 raised to X over concentration of A in experiment 2 is the same, raised to X. Now, wait this, concentration of B in experiment 3 is 0.50 raised to Y. Concentration of B in experiment 2 is 0.25 raised to Y. K and K will cancel, all right? And for A, this will cancel as well, they'll go away. And what will remain with is 0.50 over 0.25 raised to y equals to rate 3. From here, rate 3 is 2.2 times 10 raised to negative 4 over 2.2. It is 2.2 times 10 raised to negative 4. It's the same thing. Cancel that. This will be 2 raised to y equals to what? Equals to 1. It's the same thing. You know from math that any number raised to 0 is that number, so you can figure it out that. But in the event you want to use logarithm, this is going to be y log 2 equals to log of what? Equals to log of what? Log of 1 is, is 0. And any number we divide 0 divided by that number will just be 0. So this is log 2. And this is 0. So y equals to 0. I know the reaction orders. So if I go back to, my the question here, what is the value for rate constant? This is the setup, and I'll just divide the rate. You can pick any experiment. You can use experiment 1, experiment 2, experiment 3. At this point, for rate constant, you use any experiment. So if we can plug in, all right, experiment 3, which is 2 from experiment number 3. You can say 2 times 10 raised to negative 4 over, we know A in experiment 3 is 0.5 raised to 1. And if we raise B 0.50, it's just gonna be that number. It's just gonna be that number. So the rate constant is 1.1 times what? Times 10 raised to negative 4. This is the rate constant. Sometimes some others have seen they use the units when you divide molarity and molarity, but mostly you just have the value, put the value in there. So that's how method of initial rate works in determining the reaction orders. Any question on the method of initial rate? Any question on the method of initial rate? If not, I will just go to the simulation and show you how you will collect the data. All right, how you will collect the data and proceed with the calculation of reaction orders. In this lab, all you have to do is determine the value of X and Y. That is the reaction orders. So here is, all right, here is what you need to show me the calculation. And please check the rubric on how I will create your work. I've created some previous work, and some people forget to put the what? To put the calculation in there, to find the average. It's in there. You should not forget the units. So before I walk you through, Luke has a questions. Yes, so does the concentration need to be constant? Yes, it has to be the constant. If you're looking for, look, sorry to have missed your question earlier on. I hope you are asking whether this concentration with respect to each of the reagent. Yes, it has to be constant. It has to be constant.
Yeah, that's what I was asking.
Okay, thank you. So if you look, that's the criteria you're gonna be using. And for our case, you're gonna find, if you look at the reaction here, PC, this is one of the reactant. A is one of the reactants. Look at this, PC, A, you'll find X and Y using the same way. In the worked example, we were given the concentration. So the rates I've been talking about in the example, if you look at the rate right here, R1, R2, this is the values you will get. And here is the average time, to get the rate of reaction is the concentration over time. So let's see how you're going to collect the data here first before I walk you through it. You will fill in the table right here for part 1, part 2 from the simulation. Okay, let me just do something here. Mute everybody. I see some background. Okay, so that is. Can you hear me? So that is. Let's see the experimental setup. I'm just gonna go to simulation. There is a simulation here. You will go to the rate of reaction, reaction rates right here. This is where you need to go. Go to reaction rates. See, we're gonna play this, so it's gonna work. Let's see, this is gonna allow me to download. Yeah, the from my Mac computer, I cannot play that, but to get you started with how once you get the Java install, there is a link. I know some of you may encounter the same problem I'm encountering right now. You will. There's an echo. Can you? Hello? There's an echo. So the simulation here will allow us play there's an echo. All right, let me just log off from my Mac computer. I don't know if it's the Mac computer giving us problem. I want you to come back to the same conference on my PC. I'm going to log on my PC. There is an echo which I don't know where it's coming from. All right, I will just log out, and please come back again on the other. I'm just going to go on. There's something wrong with my Mac laptop. I'm just gonna log in from the PC, and I want to walk you through the experiment and play the